This video is about complex numbers. We're going to start with a definition, and that is of what's called the imaginary unit or number. And so specifically, the square root of -1, which we would have typically said is not a real number up to this point, is now getting a special name. We're going to call that number the number I. Another way to say this would be that I squared, of course, assuming I is the square root of -1, would be -1. So this imaginary unit allows us to handle these kinds of numbers in a more specific way, which it turns out has many applications, but we're just working with the simple algebra of it at this point. Now, we're going to add another definition, which is a complex number is of the form a plus bi, where the first term is called the real part, that's like the a, and the second term, the bi, okay, remember referring to I above as this imaginary unit, that's called the imaginary part. So every complex number actually has two parts. Now, let's try to use the definitions we've written here to simplify some expressions and do math with complex numbers. Let's begin with trying to simplify our first example, which is the square root of -49. Now again, up to this point, we would have simply said, oh, not a real number, can't do it. But now that we have a way to handle this negative sign under the square root with this imaginary unit, we're going to do so. Now I'm going to go nice and slow on this one. You'll recall that with our root properties, I could think of the square root of -49 as the square root of -1 times 49, and then given our root properties, I could split that up to be the square root of -1 times the square root of 49, which, okay, now here we're seeing this negative, or square root of -1, that's what we said above, is the imaginary unit, that's I, right there, as we defined it above. And then at the, secondly here, we have square root of 49, well that's just 7. So then typically we would write this as 7i. Kind of like usual, we put the numeric coefficient in front of the variable. Okay, so here I is not just some generic variable like x. It actually represents the imaginary number unit as we defined it above. But that's how we can now simplify something that we would have typically said is not defined or not a real number. Now we'll say, oh, it can be written as 7i. Secondly, what if we had negative square root of -300? Well, if we tried to do some of the same kind of work with this example like we saw previously, first of all, the negative out in front could just stay out in front. And then underneath this root, there could be a couple ways to split it, but let's go ahead and target one of the biggest perfect square factors of 300, which of course is 100. So instead of writing -300, let's write it as 100 times -3, which is really -300. As we saw done in the previous example, we could proceed by splitting up the square root of a product to be a product of square roots. So I could make this, I'll keep the negative sign in front, and then I'll make this square root of 100 times the square root of -3. That's just using one of our root properties. Then I could continue here to make this negative, and then square root of 100 is 10. So we have -10, and then we have the square root of -3, but given what we saw above to define the square root of -1, we could call that just the square root of +3 times I, right? Where this I represents the square root of -1, which is kind of not really hidden, but it's inside the root here in front of the 3. We just don't have to write out as much detail as we did in the first example every time. We can just kind of turn that into the I that we see here. Okay, at this point, we're about as simple as we can get. Now, you might normally see this rearranged a bit, where the I is typically not on the end of the right side of a number, because sometimes it gets confusing as to whether it's supposed to be underneath the root or not. So you might more normally see this written as -10i times the square root of 3. But the point is, all these are being multiplied together. This is -10 times I times the square root of 3, ultimately for our result. Let's try some more examples. In this next set, we're going to add or subtract complex numbers. Now remember, we defined complex numbers above, and in our first example, you can see here a complex number minus a complex number. Remember, a complex number simply has the a plus or minus bi form to it. And so in this case, we have the first complex number is -7 plus 5i. That's in parentheses. Then we're subtracting another complex number in parentheses, which is 9 minus 11i. Now, though we've defined this letter I very specially above, and made clear that it's not really just another variable like an x or an a or something, it has more meaning to it. It actually behaves kind of like a regular variable in the context of these algebraic arithmetic problems with complex numbers. So what I mean is, we're going to approach this problem almost like we would as if the I was a regular x. We're going to distribute this negative sign in front of that second complex number and then combine like terms. So if I rewrite this as -7 plus 5i, I'm not using parentheses now though, and then distributing to the second one, I'll have -9 plus 11i. Without the parentheses, I could just look for like terms and combine them. So like the -7 and the -9 will combine to be -16, and then the plus 5i and the plus 11i would end up as positive 16i. So -16 plus 16i would be the final complex number form. Notice it's like the a is -16 here, plus bi, the b is the positive 16. Our second example is a sum of two complex numbers. The first one is 4 plus I square root of 5. The second is 8 plus 6i square root of 5. And in this case, with a positive sign in between these two complex numbers, there's nothing to distribute. We can simply combine like terms as we see them. So notice there's a positive 4 and a positive 8. This would make up the numeric real number coefficient, the a, in the a plus bi form. So 4 plus 8, of course, would be 12. Then we can add the like terms that are listed in the second spot, the second term of each of these parentheses here. Of course, these are the I terms, the imaginary parts. But notice that I'll have to combine them as like terms. I have I times the square root of 5 plus 6i square root of 5. Well, given what we know about like radicals, we actually could combine these. And then I plus 6i would be 7i. And then square root of 5, since those like radicals are just root 5 both times, we can combine them to get 12 plus 7i square root of 5. Turns out we can also multiply numbers in complex form, and it looks a lot like some basic algebra. So when I have 8 minus 4i in parentheses times 3 minus 2i in parentheses, that's like foiling expressions for polynomials that we've been doing for a long time, except now, we have this I variable, and it means something very specific as defined above, but we do the problem basically the same way. We're just going to foil these two expressions together. So first times first, 8 times 3 would be 24. Outer times outer, 8 times -2i would be a -16i. Inner times inner, -4i times 3 would be a -12i. And then last times last would be a positive, so plus. And then it would be 8i squared. Be careful on that. So it's -4i times the -2i would be positive 8i squared. Now, we're going to simplify this, but let's remember a couple key things. First of all, we have like terms in the middle that we can combine. So let's rewrite this as 24 and then minus 28i. That's just combining the -16i and the -12i. But then at the end here, we have this 8i squared. Don't forget, as we said above, I squared is really just -1. And so we're going to rewrite it as that to be able to combine and finish this, right? This is really a 24 and a -8. If we put those like terms together, well, 24 plus -8 is really just 16. So we really have 16 minus 28i as our final result. Of course, that's in complex form. There's the a plus or minus bi. And so we have that simplified. Our next example is a single complex number in parentheses that is squared. So in parentheses, we have 5 minus 3i, And of course, there's a squared or power of 2 outside on those parentheses. Well, like we know from algebra, that really means 5 minus 3i times 5 minus 3i. Squaring means you're writing out 2 of these, and as you know, we have to be careful with these and FOIL them out. You cannot apply the squared number to both of those terms inside the original set of parentheses. It does not work that way. Rather, we have to multiply them out like one with the other and FOIL them. So first times first is 25. Outer times outer would be a minus 15i. Inner times inner is the same thing, minus 15i. And last times last would be plus, remember that's negative times negative, plus 9i squared. Then we'll combine like terms. Notice we have some like terms in the middle, the minus 15i's. We'll combine. So really, we have 25. But remember, this is actually, well, let's rewrite this one more time. So we have 25 minus 30i, combining those middle terms. And then it's really plus 9 times negative 1. Remember that I squared is really just negative 1 as defined above. So now if we put this in order where it's like a plus bi form, the a value, the real part, will be the 25 combined with the negative 9. So really that's 16, 25 minus 9. And then we have minus 30i as our imaginary part, and that's our simplified complex number. Now, when you see an example, as our third one is, which starts as the square root of negative 9 times the square root of negative 5, I want to be careful to point out one distinction that could cause this to go badly. It's possible to think of this, in fact, I'm going to write this out over here. It's possible to think of that as, oh, if I had a square root of negative 9 times the square root of negative 5, then given our square root or our just root rules that we've been discussing, you could say, oh, that's really the square root of negative 9 times negative 5, right? You can multiply what's underneath the roots together. Then you would say, oh, that's really the square root of 9 times 5 is 45, or negative 9 times negative 5 is positive 45. So you might say, okay, this simplifies to positive 45, done. However, that rule that we use in the middle of this way of doing this, combining rather, multiplying what's underneath those roots together, that actually only works if what's underneath those roots are positive. If you look carefully at math textbooks, some of them actually state this, they should state this. This rule doesn't apply if what's underneath those roots is negative, as it is here. So actually, we're going to have to say no, this is not a correct way to do it. Rather, we're going to multiply these together after converting them into imaginary form. So instead of the square root of negative 9, we're going to make that the square root of 9 times I. Okay, instead of the square root of negative 5, we're going to make that the square root of 5 times I. And then in so doing, we can reduce more. The square root of 9 is really 3, so we have 3i times the square root of 5i. Now we can multiply the numeric factors together, so 3 times the square root of 3 times the square root of 5 is just 3 root 5. It doesn't really get any simpler than that. And then I times I is really I squared, but we know that I squared really means negative 1. So this is really altogether negative 3 root 5. So again, that I squared is really what turns into the negative sign up front. And you can see that's much different in contrast to the square root of 45 that the other method got. And I wanted it just to be clear to point that out, that this other way of doing it is not okay. It doesn't actually work. So be clear on this kind of problem here. Let's try another example or set of them where we want to simplify to a plus bi form. That's our regular complex number form. But this time we're starting out with our first example being a fraction where the numerator is 5i and the denominator is 2 minus 3i. Notice that it's a fraction that is a single term. We'd like to get it into a double term complex form, a plus bi. Well, what we're going to have to do to get it there, which is not obvious unless you've seen this a time or two, is we're going to multiply by the conjugate, which is the same thing we did when rationalizing. You may recall rationalizing a denominator where we multiply by a conjugate. So let's rewrite, I'm going to rewrite and copy this whole problem out again. So we have 5i over 2 minus 3i. That's the original problem. Now we're going to multiply by the conjugate of that original denominator, which, as you may recall, it means you just change the sign. So we're multiplying by 2 plus 3i, but we do that on top and bottom. So this here is called it's actually called the complex conjugate. Okay, but it's called the conjugate, and we've seen that before in rationalizing. That's what we're going to multiply by. Now let's see why that actually works. If we multiply across the top, we'll distribute the 5i to both terms that follow it, which would of course produce 10i when it hits that 2, and then 5i times positive 3i would be a plus 15i squared. Then down below, we'll be foiling these conjugates together, but as you may recall with conjugates, you can write out all the detail with foiling if you'd like, but outers and inners will always cancel with conjugates. So that means we have first times first, which is 4, and then outers and inners will cancel. Last times last will be minus 9i squared, and then we can try to put this all back together by simplifying the numerator. Notice the 15i squared. Remember, I squared is really a negative 1. So that's really a negative 15 plus 10i in the numerator. If I just rearrange the order there to put the real number, the a part first. So it's like a plus bi there. And then down below, we can combine these. This is really 4 minus 9 times negative 1, which is really 4 plus 9, which is really 13. So let's write this out. 4 plus 9. All right, so this is really negative 15 plus 10i over 13. Now, to really force this into the a plus bi form, you could do so by converting it into negative 15 over 13. That's just giving the first term in the numerator its own denominator copy, which is valid in reducing these kinds of expressions. And then plus, and then the second term, its own denominator as well, but we could write that as 10 over 13i. So now it's kind of like we've forced it into the a plus bi form, and this might be the more common way to see it, but really it's acceptable in other algebraic forms that are equivalent. So we'll leave it as this negative 15 thirteenths plus 10 thirteenths I. Again, just kind of noting that that's the a plus bi form that ultimately we'd be going for in a problem like this, as specified in the instructions. Now our second example begins as a fraction, but this time it's 5 plus I in the numerator and then negative 4i in the denominator. In this next example, in order to turn this into a plus bi form, which wouldn't be quite obvious perhaps at the beginning here, in the previous problem we used the conjugate of the denominator, but this is now kind of flipped upside down. We have the two terms in the numerator. So this time we're gonna rationalize this as, well, we're going to treat this as if we're rationalizing the denominator, which is now a single term. You may recall that we did some of this in the rationalizing topic. We're going to try multiplying simply by an I, but of course we have to do that top and bottom. Now let's see why this might be useful. On top, if I multiply by I would have to distribute that to both terms, which would give us a 5i plus an I squared. Down below, we'd have negative 4i times I, which would be a negative 4i squared, but now let's remember I squareds are really negative 1, so this is really on top a negative 1 plus 5i, and then down below it's really negative 4 times negative 1, which is really a positive 4. And so again, we could force this into the a plus bi form by splitting this up and making it negative 1/4 plus 5/4 I to finish in the a plus bi format that we were looking for there. Now, the third example is going really to allow us to apply what we know about exponents more so than the imaginary unit, though it certainly involves the imaginary unit. This example says simplify, and then it gives us I to the 46th power. Okay, so think about this for a second. You want to try to simplify this as much as possible, knowing that, let's recall that I squared is equal to -1. We talked about that way at the beginning when defining the imaginary unit. Okay, so we could utilize that, or we could even use some more, or I guess a bigger shortcut. If I squared is -1, then what is I to the fourth? That'd be like squaring both sides in this previous step, right? So if I squared is -1, then I to the fourth would be squaring that, which of course would be +1. So one way to break this problem down would be to say, okay, I to the 46th, isn't that really just I to the fourth to some power? Or maybe if not exactly to some other power, if 46 is not divisible by 4, then maybe it's something close, and then we could finish the rest by using some power of 2. So let's consider for a moment, 4 times, we'd be multiplying exponents in this scenario. So 4 times 11 would be 44, which is close, but I want 46. So I could say I to the 46th really is I to the fourth to the 11th power times I squared. Okay, so to be clear, that really means I to the 44th in that first factor times I to the second. I would be adding the 2 with the 44 to get the 46 that we started with. But the reason this is convenient is because now I can say, wait a minute, I to the fourth, as we just said earlier, that's really just 1. So this is really just 1 to the 11th times I squared. But wait a minute, I squared is really just -1. So 1 to the 11th is 1 times -1. Of course, that's just -1. So really, I to the 46th power is -1. And you could do this really with any power of I that you'd like. Of course, if it's an odd power of I, you will likely end up with an I in your actual answer. But if it's an even power, you should be able to use, powers of 4 and 2, like we did in this example, to boil it down to a single real number.